All right. Focus up here, please. Okay, so quick review. Now, a lot of people have gotten through these, but there's still some people. I think there's some questions out here. So let's take just an opportunity to quickly review the linear system stuff. Our week, I'm going to be gone Wednesday. So what I'm going to do is I'm going to start something today. We'll just introduce it. We'll go through a little bit. We'll finish it up tomorrow. You'll get some time in the lab tomorrow to work on it. Wednesday, I'll be gone. I've got the lab scheduled, so you'll be able to work all day, kind of, amongst yourselves, helping each other out, working on this stuff on Wednesday. And have everything due through the assignment that I'm giving you today, or the one I'm starting today. All that stuff's going to be due Thursday, including all the other stuff that I had a due date of, I think, tonight. It was either last night or tonight. I can't remember. I'm going to push all that off till Thursday, though, because I just want to make sure with this review stuff I'm able to get questions answered, okay? Questions on that? Good. Okay, let's talk about these. Let's take the first one. Okay, on this first one, you've all had a chance to look at this now. How am I going to do this? How am I going to approach this? What method am I going to use to solve this linear system? Substitution. Very good. How come? Okay, good. It's easy to isolate one of the variables, and in this case, it's already isolated, right? So when we have a variable isolated, what do? What am I going to mark up here? I'm going to substitute, but before I even begin that, I kind of want to highlight the fact that that's done. What do? It's been a week. Well, okay, I'm going to use parentheses when I do the algebra, but I'm going to put a box around it. How come? So I'm coming back to it. Yeah, that's going to be an important equation in just a little bit. We're going to come back to that several times. Okay, so that's our substitution equation. So now we're going to go ahead and do the substitution. So we're going to start with our other equation, and 2x minus 3. Now here's my substitution. What am I substituting for y? So okay, good. The 2x, whatever y is equal to in this case, so the 2x minus 1. And let's see, the top equation has all that being equal to negative 5. So next step. Oh, actually, before we do that, let's take stock here. How many different kinds of variables are there? Not how many different variables, but how many different types of variables are represented in this equation that we've created? Say it again. 1. Yeah, x, right? That's the whole point. By combining these two through substitution, we've eliminated one of those variables, so now we can solve this. And I know I said this a lot, prior to Roundup, but I'm going to say it again because it's so important. Whenever we have an algebra equation with only one kind of variable in it, that's good for us. That means we can solve it, right? Turns out, and we'll talk a lot more about this, a little bit this year, a lot more next year, we can solve any system of algebra equations as long as we have at least as many equations as we have different types of variables, or we call them unknowns, right? So in this first system up here, I had x's and y's, so I had to have at least 2 equations to be able to solve this system, which I did. I started off with 2 equations, so that's enough, okay? Now let's do the algebra. Okay, so let's go ahead and solve for x. What do we do? What are we going to do here? We're going to simplify. Good. And specifically, what do I have to do to simplify here? What's the first step going to be?
Distributive property.
Good. I'm going to distribute the negative 3. Very good. So that's going to give me, I've got my 2x. What am I going to get here?
3.
When I distribute that negative 3 to the 2x, what do I get? Negative 6x and what? Okay, good. Because when I distribute a negative times a negative is positive. So that's a plus 3 equals negative 5. Okay, we can be efficient here, and we can kind of combine steps. Our goal is to get the x by itself on one side, right? So that means we want to get everything else on the other side. So what can I do? I can do 2 things at once. What? Okay, I'm going to subtract the 3 from both sides, which means I'm going to keep the x's on the left then, right? That's fine. So those go away. On this side, I'm going to get negative 8. Good. And if that's sometimes, I know that doesn't seem like a big deal, but sometimes this trips people up. Remember that whenever I am subtracting something, I'm just adding a negative. So the other way we could think about this is negative 5 plus negative 3. which is negative 8, right? What about these guys? What do they combine to? 2x minus 6x. Same thing as 2x plus negative 6x.
Negative 4x.
Negative 4x. Okay, so that's getting easier. Last step. Okay, we got to be careful of the sign rules here. If I divide a negative by a negative, I get positive. So 2. Okay, good. We got x equals 2. Now what?
Plug it in.
Now, we put a box around this for this reason. Now we're going to go back to the boxed substitution equation and plug in. Okay, so if we do that, we get y equals 2 times x is now positive 2 minus 1. So what is that? Yeah, 2 times 2 is 4 minus 1 is 3. So how do we write our answer then? How do we write the solution to this system? We know x is 2 and y is 3. That's correct.
2, 3, 2.
Yeah, we have to write it as an ordered pair. Good. Okay, what is the significance of that ordered pair in terms of the graph?
That's where they intersect.
Yeah, it's the point of intersection, right? This is a line and this is a line, and they intersect there at that point. Okay, good, good, good. Is that coming back? Maybe it never left, but I just want to make sure. It's been a week. Okay, so how about this guy? Okay, is that second example, is that a good candidate for substitution? Now, people are shaking their heads, and that's correct. It's not. That substitution, we could make it work, but it would be miserable. I mean, we have lots of fractions. It wouldn't be very fun. So what do we do instead? Okay, we're going to use elimination, linear combination, whatever you want to call it, same thing. This is where we have to think a little bit before you just jump ahead. What's our strategy for elimination? It really pays off to kind of think ahead and think what you're trying to do so you can pick the easiest way to get there. What's our goal with elimination? We want to eliminate a variable. We want to be able to multiply one or both of these two equations through by some number so that we can set up either the x terms to cancel or the y terms to cancel. It doesn't matter. Pick the easiest one. So any suggestions? They don't cancel now. What could I do? What do you think, Bailey?
Multiply the top by 3.
Okay, top by 3, bottom by 2. I like that. Oops, 3, not 2. Minus. Good choice. Why do you suppose, why is that such a good choice? It's not the only choice that would work, but why is it a good one? Probably the best one. I don't have to deal with negatives. Good, there's one thing, perfect. So I've already got, I need to end up getting a negative and a positive that cancel. Well, the top was already negative, the coefficient of y, and the bottom was positive. And the other part of that probably makes this a really good choice? What else? Small. Yeah, use the smallest numbers you can, absolutely. So what do we get? If we distribute that 3 all the way through, what do we get? 9x minus 6y equals, yeah, how'd you get that? We can do that in our heads. How come? How can we do that? You could, sure, you could act like it's 30 and subtract 3. That's fine. That's a good way to do it. So negative 30 times 3 is negative 90. Take one of those 3's back. What's another way you could do that? How could I break up this 29 into numbers that are easy to multiply? 20 and 9, right? 20 times 3 is 60. 9 times 3 is 27. 60 and 27, 87, right? And it's negative because of the sign. On the bottom, if I distribute the 2 all the way through, what do we get? 8x plus 6y equals, okay, and we got what we wanted, didn't we? We got the y terms are opposite, so they add to 0, they cancel. So if I add these up then, what do I get? 17x equals, so if I divide by 17, what do I get? Negative 5. Yeah, it goes in evenly, so I get negative 5. Okay, I'm halfway there. Now what? Yeah, I gotta plug it into one of them. It doesn't really matter, just choose the easiest one. You know, if there's not an obvious easy one, it doesn't matter at all. I'm gonna pick the bottom one just because I don't have a very big number on the right. So if I plug that in, 4 times -5 plus 3y equals 1. What's 4 times -5? What are the 2 steps in order to isolate y there? First, you gotta do it in the right order. If I wanna get x by itself, or y by itself, what do I have to do first? Yep, add 20, good, get rid of that, and then divide by 3, and that gets the y by itself. So if I do that, 1 plus 20, 21, divide both sides by 3, and y equals 7, good. So my ordered pair then is what? Good, okay, that's my answer. Okay, is that making sense?
Yeah.
Okay, what about situations like this? What if I get weird answers when I'm all done and I'm gonna try to solve the system and the variables all disappear and I just end up with an answer like, for example, 3 equals 3. How do I interpret that? Say it again. Infinite solutions, good, because it's always true. And so that tells us that we've got, you know, that symbol means infinity, you probably know that, right? So we get infinite solutions, and how do we interpret that in terms of the 2 lines in the system? Same line, good. So infinite solutions, same line. What if we get a weird answer that's not true? No solutions. And what's that tell us about the lines? Parallel lines, very good. Okay, good. So what I want to do today then, I want to just start talking about our other kind of big topic that we're going to review. And we're getting pretty close to being done with the review, algebra review. This is an important one. This one is factoring. You probably remember doing some factoring last year. Oops. Okay, I think a lot of times, raise your hand if factoring was one of your favorite algebra topics. Raise your hand if it was one of your least favorite algebra topics. And usually I would see some hands go up here. People that are brave enough to raise their hands would say that's probably the case. I think there's a reason for that. I think it can be a little tricky, but I can make it pretty simple for you. I think we're going to review, you know, bottoms up. You learned that last year. Bottoms up is great. That makes it really simple. So we'll review that process, because that takes this normally fairly complicated process and really does make it simple. But I think the other reason that sometimes people, you know, just have a hard time and are just really don't care for factoring is, you know, they're not even sure why they're doing it. Why do you factor? Why is that important? There is a motivation for us to factor things, and this is it. If I can get this thing, if I can take this expression, and this is a quadratic expression, by the way. Probably remember talking about this from last year. Anything that looks like this form, ax squared plus bx plus c, where a, b, and c are just numbers. That's a quadratic expression. And what's different about that than what we've been talking about is obviously the x squared, right? That's what makes this a little bit different, a little bit more complicated. Our goal here is we want to see if we can break up this quadratic expression into a product of small, easy factors. That's the whole point. We want to take this one big expression and make it a product of 2 smaller, simpler expressions. Why? Well, if we can do that, it's helpful to us. Now, in order to, you got to kind of warm up your brains a little bit though for this. So, pencils down. Just this all in your mind here. So I want you to just kind of keep track of the number as we go. So we're going to start out, we'll start easy, like 2 plus 4. And everybody's got in their mind 6. So when I say times 9, what do you get? So you had a 6 times 9, 54, okay. So let's say minus, now just do it inside your head. So we're at 54. minus 11, okay, plus 5, okay, times, 17.145. I'll give you an extra second. Okay, got that. Times, 1,395,471.943. Hurry up. Okay, times 0 is what? Okay. It didn't matter how complicated the rest of it was. The key there is what? How do I get an answer of 0? Multiply by 0, right? And so where this is important to us is if we're trying to solve an equation like this, if we're trying to solve an equation like, say, x squared plus 7x plus 12 equals 0. That's what we'd call a quadratic equation in standard form. It's all set equal to 0. We'll do, this is kind of a next year topic. We'll spend a lot of time talking about this next year. You talked about it a little bit last year. Well, how are we going to come up with solutions to this? Remind us real quick, what does it mean to be the solution of an equation? So if we want to find the solutions of this equation, what are they going to look like? What do you think? The solutions to this quadratic equation. Sounds complicated. What are they going to look like? X equals something, right? Probably. We got x as our variable. What do they have to do? If it's a solution of that equation, it's going to be a value of x, but what does it have to do to this equation? What do we always say about solutions? Solutions are values of the variable that do what to the original equation? Make it true, or satisfy the original equation, right? So they're going to make it true. That's hard. The other stuff we've dealt with earlier has been relatively easy. We've always dealt with these linear equations, and it's been relatively simple for us to isolate a variable and get it by itself, right? Been pretty simple, just by working backwards through order of operations. Well, that doesn't apply here, right? The reason it's worked so well in the past is we've always been able to simplify our equations so that we ended up with a single variable that we could point to and therefore solve for, right? And that, you've heard me say that prior to Roundup. If you can point to a single variable in an equation, you can always isolate it, right? I can't do that here though, right? There's only one kind of variable, it's an x, but what's the problem with this? Why can't I put that together and only have a single x? Because I've got one x squared term and one term that's just got an x, a regular x to the 1 power. They're not like terms. They can't be combined. So I can't use my old strategy. I can't just isolate x there, right? I've got to do something different. It's a hopeless strategy to just try to randomly pick numbers. In this case, we probably could get it if we just tried numbers, because I made one that's fairly easy here. But in real life, that's almost never going to happen. What if the solutions are random decimals, or they're irrational numbers, and they're square roots? Or we'd never guess that stuff. There's an infinite number of possibilities. You can never hope to get it right. So that's not a good strategy. We've got to come up with a different strategy that's going to work. Well, the strategy is what we just talked about. We know that if this is equal to 0, right, if the whole expression is equal to 0, if I'm able to break this up into a product of two small simple factors, when would the product of those factors be 0? There's only one way you can multiply stuff, right? Because this implies that I'm multiplying these two factors. What's the only way I can multiply factors and get an answer of 0? If I multiply by 0, right? So I know then, this is called the zero product property in algebra. I know that the only way that this can ever equal 0 is if this little nice easy factor equals 0, or this one does, right? So what I'm really doing here by factoring is I'm trading this one impossible quadratic equation for two really simple equations when I set these equal to 0 that I can solve easily, right? So there's our motivation. Now let's go back and kind of review how do we do this stuff. Okay, if we want to factor this, we can really break this into two categories, the easy kind and the hard kind. What's the value of A, B, and C for this quadratic expression? A is, what's A?
1.
Okay, and we know that because if there is no coefficient in front of something, it's always an implied 1, right? We just don't write it because we don't need to. So A is 1, B is 7, C is
Well,
12. Whenever A is 1, that's great news, that makes it easy. If it's going to factor, and it won't always factor, and if not, we'll just try some other strategy. These will all work for now. I mean, I'm gonna give you ones that work, that factor. If A is equal to 1, I know, guaranteed, that this is gonna fit the pattern. When I break it apart, I'm gonna get x plus or minus some number times x plus or minus some number. These are both gonna be x's, and if you think about it, it makes sense, because I've gotta be able, when I multiply these out, I have to get this answer. And if I FOIL these, x times x is x squared. It's the only way I can get x squared is if I have x times x, right? The question though is, what are the other numbers, right? It's easy to find. Do you remember the rule for finding the other magic numbers that go with the x's? They have to do what? Okay, yeah, it has to do with the 12 and the 7. Which way is it? They have to add to 7 and multiply to 12. Right. Does that make sense? Okay, we're out of time, aren't we? Okay, we'll pick this up tomorrow.